you. First of all, I would like to thank the organizer for this conference and, of course, to many other people that this project just make it happen. And I would like even thank Karo, because when I was writing my presentation, just thought always about what should put, because I should mention many more things than I can have any time in that. So he just introduced many questions about Artemis, about AstroAccelerate program, probably a little more, low-far and polyphase filter, which is just about that. And I should mention about something that he just on the last slide showed, the Xeon Phi, and that's just something really interesting, I think. But first of all, I'm just doing it here a little bit. I don't mind. First of all, I will make a short, just a few slides about HPC, which is just abbreviation of high performance computing, and probably many people ask me why we need that, why we need more power, or why we should mention something like that and use high-performance computing, some powerful machines. Well, I think there are two reasonable answers. Just, if you look, you can just have the same problem, and the solution you can have in quicker time, in less time. You get your results quicker. Or, there's another way. You have a bigger problem, and you want to know the results. Well, we are not now in the era where we are hacking some system banks and so on, so probably some people want that. Of course, high-performance computing is really big and machine and many money is there. And you can see that many countries, just in many other fields, in medical science, engineering science, you can just forecast, you can compute what will be tomorrow, how will it look like. Or some seismic exploration, or even, as I mentioned, the medical imaging, medical science, medical imaging, or, is it pointer? Oh. Or just drug discovery, of course. That's really nice. This picture is just from Oak Ridge National Laboratory. It's just a really nice thing with many people who involve the money wants to see something, visualization. So this is just called Everest, visualization data for the science. It's they are working here. Just a nice picture, I think. Yeah, there exists a really nice website called top500.org. And this slide I just show because there are 500 most powerful machines on the world. And this is showing just the difference by countries. You see that United States absolutely win. Well, we compute some China, and probably some European country, you get really nice number too. High performance computing and the most powerful machine, United States, usually they're using it for national security, for military science, and anything else. It's top secret sometimes. And of course, China too. Even some in China, I think there are some astrophysics, evolution, galaxies, and so black holes, and so on. I just pick up two most powerful machine by November. This is just by this November. China is now on the first place. It's called Milky Way. It's Tianhe, the second age. Well, they invest really lots of money because they wanted to be in the first place. Just want to mention it because there's something called 16,000 computer nodes. It's the mini-core system there. There are two Intel Ivy Bridge Xeon and 3 Xeon Phi chips. This is the Intel coprocessor I will talk about later. This is the theoretical peak performance you get. Just crazy petaflops. Well, it's nice. It's the amount of money you can get here. And here's the second. was just an old one transformed to a new one. The old one was called Jaguar, and the new one is just Titan. It's I mentioned it in Oak Ridge National Laboratory. They have a little different way how to do. There's 18,600 so on nodes, but there are AMD processor, not the Intel one, and there are GPU cards, NVIDIA cards. Of course, this speed is little low, 12, I think. It's based on some LinPack computation, just linear package for arithmetic and so on. And here are the two things in many core system nowadays. I think scientists are just looking for one from Intel and one from NVIDIA. Well, there's even some from AMD, but I think they missed a little the train because it's going a little slower. They're using for rendering mostly. It's called Fire Pro, I think. Well, you see here the Xeon Phi processor, and here is just usual graphic cards. You probably know because most of us have some computer, personal computers or something like that. It looks similar, but the construction is really something different. Here's a GPU from Fermi generation. It's just not the new one. The new one is called Kepler. And I just want to note some structure of that. Here's something called the multiprocessor. Multiprocessor is divided on some other feature, probably a little too small. These pictures just show that you have 32 cores. Here's just the structure of the core. You see that it's really easy, and you can do only floating point or operation really simple. The graphic cards are used for in flame taxonomy about single instruction, multiple data. You just use the same instruction on different data. Here's just some type and just some interesting way. You get some about 1 teraflops peak performance, just how much costs per watt, which is what is really interesting because we want to know have more flops per watt. And here's the bandwidth. Carl mentioned that in some problems they are really interesting to see the memory bandwidth. And the capacity, which I will want to point here, see is really slow. Well, it's not so big, 1.5 gigabytes. Well, it's not so much. Well, you put the single multiprocessor there, and here's the structure, the block diagram, how it's constructed in Fermi generation. You have up to 16 multiprocessor. So you can run about 512 core. That's the many core system. Many of us have laptops, tablets, and smartphones. And of course, too, of course. There's something different between many core and multi-core. I don't see any point why they just choose because many core are just from 64. How many core should I have to have a many core system? Well, you can use for high performance anything like that, even your laptops. You just need to know about something more about the processor, about what you have inside the hardware. Okay, let's look on the Xeon Phi. And we started before with the computation, they call it CUDA, the language. They started around 2006. Intel started too, but was more private. In fact, the last year they just put the Xeon Phi that everyone can buy it. Well, it's costly. It's around $2,000, I think, on cards. But you have the peak performance a little bigger. You have not so much about the watts because there was around 5 gigaflops per watt. And you have bigger bandwidth, which is really interesting. And of course, you have more memory capacity, which can be good if you want to transfer bigger data. Here's just the structure as I showed before. This is mentioned if I turn back. This is one core. This is core of the Xeon Phi. You see the difference. Just more, well, it's not so, it's not simple as on the NVIDIA core. Even there is just some units, vector units, you have divided here. So this is small thing, it's just expanded here. And there's the magic, because you can run about 16 floats per one cycle there. And you have around 2 threads, I think, per core. So you can run around 300 core, because they have the cores, the structure. There's a ring interface interaction between the cores. Then I have around 60 cores of this structure. Okay, I talked a little about Xeon Phi and many core system, and from the NVIDIA side, the GPUs. And I will talk about optimization of your code. It's a really interesting way. You should think always when you do some numerical science or computational science. There's a nice cycle called APOT. Just mention it in every reference book, or some few software engineering really like that. There's an acronym for assess, analyze, parallelize, optimize, and deploy. There's a cycle. If you do some new job, you have some interesting problem you want to compute, you should mention something where I can get the power from the many core system. Where can I get the parallelizing or optimizing? Well, there's the process here. And there's the parallelization. What can I use? I can use Intel intrinsic as an AVX flags, or I can use GPU, or I can use Xeon Phi. What is better, what not? And of course, you can choose even the programming language, which is sometimes helpful. If you want to compute on GPU, on NVIDIA cards, you can use CUDA language, just extension of normal C. Or OpenCL, it works on AT and on NVIDIA cards. The CUDA is just proprietary for NVIDIA. Okay. Well, then you go to optimize. Just deploy some program, you get some results, and then you really shoot some report. Because many people just turning around and never get here, this point, this picture. Okay, there's something like more tell about which level you can get to optimizing the code. Just good idea is just to, if you have some algorithms, you can choose the better one for specific hardware, of course. Or you can use just some architectural specific detail, which we are using with Karel, probably. Or just use some micro-optimization, which can be really, really hard. There's something called, this is from my computer, it's a profiler. It's useful sometimes use a profiler to see the results, how it gets average time, and so on, and how you can transfer the data. It's just the process when you're computing on GPU cards. You have some main memory on the host, some CPU, you transfer to the global memory, the GPU cards, and you execute some kernel, call it kernel, some many threads, and so on. The kernel is just, you can divide in something called grid, and grid can be divided in blocks. Just execute many threads in there. Just visualization you can do in 1D, 2D, 3D. Of course, unfortunately, there are some restrict things. You need to mention if you have some typical cards like GTX 480, the Fermi generation. You have some compute capability, and there are some restricts for that. You can run more than 100 threads per block or per SM, and so on. There are many restricts. There's just a short list of that. Yeah. there's just a slide about memory, because we are using the polyphase filter and using GPU cards. We are using something in the global memory architecture, because the card's reading in cache, and he's reading 32 floats in a cache line. So we're trying to use all the cache line and compute that. AstroAccelerate is just a program from Oxford and using the thing you see before. And here's just the first thing, some results they got. There's the dispersion measure methods, they use it. You get some signal and so on. You want to transfer data and quickly, and do that in real time, really fast. You have lots of data there. And you are using something in the memory called here shared memory. Just nice thing that can broadcast. Just switch my results. Really preliminary. I did that 1 hour ago. So just similar slides on the next what Karel had. Here's just the threads, here's the time. As you saw before, there are some point where you get best results. Of course, there are some under low and so on, and powerful cost for that cache lines. Well, I put the standalone code, the serial one, the best from Karel. This is just the time, because if you increase the data size, unfortunately I cannot go more than 500 megabytes. And just not lots of memory that for the cards. Get a little better, but the scaling is not so good. That's the memory bandwidth. Well, I have a little better, but there's something peculiar. We should talk more about that. So I'm not convinced that this is true. And here's just the flops operation for this data size. Well, it seems it's 1000 nodes, it's 200, which is some log files. I would like to thank you for your attention.